Okay, so in the previous video, we were looking at a demonstration by Tabashnik and Fidel, and we were looking at change over time or in terms of computer quality or measurements of computer quality over time and over a 20-week period. And we just went through a phase of identification of the proper ARIMA model, or at least a reasonable hypothesis about what model we should be utilizing. So just remember that the identification phase involves identifying the AR and MA processes. To do that, we have to go through a phase of first determining if the time series is stationary. And if it's not, then we have to utilize differencing and perhaps even a log transformation of the difference variable in order to achieve stationarity. Through that process, we go through, or the next process involves looking at the autocorrelations and partial autocorrelations, and we can study the autocorrelation and partial autocorrelation functions using parallelogram. And through that process, what we finally determined was that there was evidence of a moving average process with our data. And so, and I also had kind of referenced this set of demonstration figures right here. And what we had decided on was that the process appeared to fit appeared to be a moving average process. And I had kind of cited this demonstration right here, and but this is an idealized version of a moving average one process, but remember we had to do a first differencing here. So technically speaking, the ARIMA model that we have would be described as 0, 1, and 1. So reflecting 0 as the autoaggressive component, 1 reflecting the first order differencing, and then a 1 reflecting our notion that this is a moving average one process. All right, so once we've sort of decided on a model, then we have to actually estimate the parameters for that model. And so what we're going to do is we can use some syntax. So I've actually kind of already generated some syntaxes here. And in their presentation within in chapter 18, the authors utilized this syntax right here. It's basically to utilize the ARIMA commands in SPSS, you're going to have to go to File, New, and then you'll click on Syntax, and it'll open up a new syntax file right here. And so basically what we'll do is we'll type in, ARIMA, and so you'll notice it highlights in red right here. And then, in terms of some of the other components, we have to have our dependent variable name, and then on the next line, we'll have a backslash model equals, and then in parentheses, we'll lay out the order for our components for our ARIMA model. So there we have the 0, 1, and 1. And then in their demonstration in chapter 18, they also included a constant. So so basically, we would just be, typing that into our new syntax file, and there you go. Now, if you don't include a period, this will appear in red, and that just means that if you run it, it's not going to work. So be sure that you include a period at the end of the syntax. This will change to blue, and then that kind of closes out the instructions. So what we'll do is we'll highlight all of this, and then we'll click our little green button, and you'll notice that there's a little bit of a warning message right here, in chapter 18 of the book, they don't really go into this warning or any of the details. They just basically kind of just kind of estimated the model and sort of went on to looking at the diagnosis of the model. So at any rate, we'll kind of just note really quickly that really what we would not be wanting, and where the problem seems to really kind of lie is in this MA process, which is you can see it's near 1, so that's creating our problem. But nevertheless, once the model is basically estimated, so we've estimated our parameters for the model, and so the next step is to diagnose the model, really kind of look at the residuals to determine if they're following a white noise process. And the way that you can do this is to go to Analyze, Forecasting, and then go down to the autocorrelations again. Now in this case, we're going to be focusing on the residuals, and you'll notice that in the data set we have, by running our ARIMA model, we get fit values for our variable as well as error. And so these are the residuals for the model. So we're going to evaluate the residuals in the model. Just kind of taking this back right here. Here are the, these are the fit values, or these are the predicted values based on the ARIMA model that we've tested. And the difference between the actual values and the fit values, these are the residuals right here. And so these are what we're going to be studying. So we'll just kind of go back under Forecasting, Autocorrelations. We're going to take the difference out because we're not doing any differencing on the errors. We're going to move quality out, and we're going to put error back in right here. Under options, just kind of sticking with their presentation, they stuck with Bartlett's approximation, so we're going to go with that, and then click on OK. So now we can see the autocorrelations and partial autocorrelations for our current model, which is the 0, 1, 1 model. So you can see right here that we still have, we have a lag 1 that would be, that's, so there's an AR1 process apparently maybe still going on with respect to the residuals. And then when we scroll down, you can see there's our correlogram. And you can see that there still seems to be a substantial process with the lag 1. When we look at the partial autocorrelation plot, though, you can see that none of the partial autocorrelations are statistically significant. Now, just so there you go. Now, according to Tabashik and Fidel, what they suggest is that you should really be kind of looking at the first 3 lags for the residuals and looking for basically forming a T ratio of the autocorrelation to its standard error. And what you're looking for are values that are less than 1.25, and for later values less than 1.6. That's what they're kind of citing. And so we can kind of look at this right now in the same way. We'll just we'll start with the first lag, and you can see that we have 0.401 negative value divided by 0.229, and it's negative 1.75. So that would be kind of indicative that we do have some autocorrelation in terms of the residuals. The latter ones don't appear to be as problematic. So what the authors actually do is they kind of decided to try a different ARIMA model, and this is the process. It's fair, it's very data driven in that you're really kind of looking at various patterns in the data and trying to arrive at a particular model. So it's not as sort of theoretically driven as I'm kind of used to. Most of my modeling of data is based on theory and testing hypotheses and so forth. And this is really kind of more of a bottom-up process because we're really just exploring patterns in the data to determine what the best ARIMA modeling process that we should utilize. So in the demonstration that Tabashik and Fidel provide, they actually then suggest, well, let's try a different model. Let's try an ARIMA 110 model. So you'll notice right here that I'm just gonna, actually kind of move down and to this next demonstration. We're just going to go with no constant right here, and or this model right here. So it's a 110 model, and in the syntax they actually include a statement of no constant. So in other words, we're not going to be modeling an intercept in this demonstration. So their first demonstration, they included a constant. In this demonstration, there's no constant that is being included. Um, and this kind of highlights a subtle point, but it's a point nonetheless that you should be mindful of. Is the question of whether you should include or exclude a constant when you are running your ARIMA models. And so I kind of worked up a little bit of a based on my reading, sort of a little description of or kind of a decision sequence for thinking about whether or not to include a constant. So I have right here process PDQ, a little bit of a description, and then should you include a constant, or is it permissible or not? So a 000 process, basically that just is, first of all, you would not want to bother running an ARIMA model if this was what you were assuming. In other words, if you were assuming a stationary process that didn't require a differencing, no autoregressive component, and no MA component. There's no need to be using ARIMA in this case, but this was just to kind of highlight, if you were running this using ARIMA and this was the process that you were expecting, you would include a constant. Now the next line right here, you've got a 010 or 020. So in other words, there's either a first order or second order differencing where only D is specified. And in these cases, you would want to include a constant for those models. Now, if you have a process where you have a first order differencing and you have AR or MA processes that you're including, then you may or may not choose to use a constant in your model. Now, if you have a second order differencing and you're still estimating P and Q, then you would not include a constant. So these are just some ways of thinking about when and when not to use a constant. So there you go. So at any rate, if we go back, then we're gonna keep in line with the presentation from Tabachnik and Fidel for right now, and we're just gonna not include a constant. So we have essentially we have an AR process first of one first order differencing, and so in this case we basically we may or may not choose to use a differencing. So, use a constant. So they chose not to use a constant. So I'm just going to highlight this and run it. And so now when we scroll down, you'll notice that we get a variety of information. We get fit statistics that are kind of useful, like particularly looking at Akaiki's information criterion and Short's Bayesian information criteria. These can be useful for making model comparisons. The parameter estimate for the AR1 process is negative 0.686, and so that this is essentially the model that we have right here, and so that's the estimate of the AR1 autoregressive component. Once again, we can look at the residuals and kind of go through sort of our diagnostic phase. So this is actually kind of overwritten what we had previously. So these are the fit values from our new model, the errors, and so now we can kind of go into analyze, forecasting, autocorrelations, and we'll just move error over here. And no differencing under options, we'll leave it as Bartlett's approximation and OK. And so here you can see that our first autocorrelation is lower than what we had previously. In our previous model, it was it was like a negative 0.401. So this is not significant. And this is what it looks like. So you can see that that first lag that was that appeared to be kind of significant in our previous run through is not so that autocorrelation is not as prevalent, and we have the same sort of situation in our partial autocorrelation plot. So um, that's sort of the rudiments of running these different kinds of models using SPSS syntax. And like I said, you sort of have to ask yourself, how do you want to treat the constant? Do you want to estimate or not? And so, as I said before, think about how you want to deal with that when you're modeling these different processes. If like in this particular case right here, if you had differencing and you're not estimating AR or MA processes, if you don't include the constant, the model won't run. So just kind of to give you an example of what I'm talking about, let's kind of go up here. I'm going to rerun this first model right here, and I'm just going to make this 0, 1, 0 process and say no constant, just to kind of demonstrate what will happen. If so, in this particular situation, if I run the analysis, then I get an error message. And the same would go if I used a differencing of 2 right here. So if I run this, I'll get an error message. So, you can see that if we choose not to include a constant and all we've done is difference our variable, um, then the model won't run. So, so now I've included a constant, and there you go. Um, so so that's the way to think about it. So we have another thing to kind of note too. So I'm going to make this 1 again, and I'll just use the 110 as we had before, and go back to no constant. Another thing is that right now the way this is laid out in terms of our syntax, this states that we're using first difference variable. So in other words, we're differencing on our quality variable, but there's no transformation of that variable. Now, if we had gone through this process where we had, decided going through our sequence charts and everything, that we had decided that we should be using a natural log transform, then if we've done that, then we want to incorporate that in our ARIMA model. So the way that we can do this is just the statement ln and then a space right here. And so this is kind of a specification that we're going to be using the natural log of our difference variable. So our first order difference variable in this case. So when we run our analysis, it will take that into account. So you'll notice the model description right here. It says the dependent series quality, transformation, natural log, constant was not included as AR1 process, and we used differencing of 1 right here, and there was no MA process. So, if how you decided to deal with the transformation of the difference variable, you can incorporate that in your syntax as well. And so if you choose to use a log transformation, just type in ln, and then you'll see it appears in red, just like the no constant. If you choose not to, and you just want to use the non-transform difference variable, then you don't really need to. Then you don't type in the ln. You just run the analysis without. So that kind of gives you just sort of a brief breakdown of how you can run the ARIMA models using syntax in SPSS.